Hello, can you hear me? Okay, thank you. All right, so let's continue. So we've just gone through the eight steps of the machine learning. So right now I'm gonna skip some of the part of the slides so that we can uh, cover the basic knowledge of neural networks before noon. So this is an example problem. I'll just skip it. Uh, and then let's talk about artificial neural networks. Okay, so the decoding algorithms for EEG has moved to deep learning recent years. Previously, people used a lot of traditional machine learning algorithms, and that works very well because EEG data is not. We don't have a massive amount of EEG data because it's not because collecting EEG data is relatively um, difficult because you need to have human subjects. You need to put a sensor on the human body, and you have to prepare a good laboratory to do so. So compared to image data or auditory data, uh, it's relatively difficult because the sensing techniques cost higher. But recently, since there are still increasing of amount of data accumulated, and so people start using deep learning methods based on artificial neural networks and to achieve some nice performance. And some of the in some type of EEG classification is outperforms the traditional methods. So artificial neural network is also called connectionless system, but they are it's much more often to call neural networks. They are computing systems inspired by biological neural networks. And so let's quickly talk about biological neural networks. So you have neural cells, they're connected to each other by the synapses. And the synapses is the end of either dendrites or axon, and dendrite axon are extents of the cell body here. Um, and we mentioned that dendrites collects information from other neurons, and the axon is for this neuron to transmit information to other. So you can convert it into a artificial neural network unit that has multiple input, and you can have a summation operation here, and to have an activation function to create an output to further neuron. And this unit is called perceptron. It's developed in 1950s. It has a long history. It's like the grandfather of all neural networks now. So it a single perception is like a linear classifier, and when you have multiple perceptron, it creates a neural network, and it can do some lots of things. And here we're gonna use it to understand the basics of neural networks. So the neural networks improve itself by a technique called gradient descent. Uh, so first, let's have a uh, quick look at the structure of perceptron. So here we have different variables here. The input variables are x, and here the w are the weight variables for the input, and then you have the functions here, the activation function, and b is the bias of the function, and y is the output. So here the y is expressed as a function, your activation function f of the input. And the input is the weighted summation of your input from 1 to d. So we can express this by a vectorized form, w1tx plus w1 naught. This is the bias. And f here is the activation function. So in this example, it's a step function. So it gives you 1 or 0. And it gives you 1 when your input reaches uh, the, the input, the weighted sum input adding with the bias is larger than 0. Then your y will output with 1. Otherwise, it's 0. So this is the basics function we can see in the perceptron. And here we're going to talk about gradient descent. The gradient descent is to find is to is a process to optimize your parameter. So using the gradient of the parameter space and to find the optimal points in the parameter space. So let's say we have a multi-layer perceptron, and here, since we have multi-layer perceptron, we need to use backpropagation to propagate the gradient from the output layer to the input layer so that the parameters of each layer can be updated toward the optimal point. So first we need to look at the error function. And now people call this by loss function more. So loss function of a neural network is the the critical function we need to uh, look at, because the ultimate goal of a neural network is to minimize the loss. So here the error function here as the loss function, we're trying to minimize this. So what we have here is the estimated y minus the actual y square and sum. So this is about for your neural network to output. So the y is the output. So if it's a classification problem, then it's a label. So your predict label has to be close to the actual label as close as possible, and that will minimize your error. But here the y is more like a continuous label. So in the example of predicting age using face image, this is the estimated age or predicted age minus the actual age of that image. And you're trying to minimize this. So you minimize the square term of this, the error. And the sum is when you have multiple uh, output node here, you have to minimize the sum of them. Okay, so anyway, we have the loss function here. We're trying to minimize it. And the way we do using gradient descent is to find the partial um, derivative of your error against your parameter. So you're looking for you're looking for. So why we have this is because in the parameter space here, assuming we have just two parameters, beta naught and beta 1, and the s is the value of loss function. So you will have a, you can imagine there's a hyperspace a parameter and you're looking for the lowest point within the space. So what we're looking for is, and the lowest point is when you have gradient equal to 0. So here what we're looking for is to have is to look for the gradient to be 0. So these are the parameters. So here, since you have two layers, the one you have the weights as v, and one the other layer you have weights of w. So you're looking for the the 0 point in their gradient. So here we have some derivation of backpropagation to show you how the error is being propagated from the output layer to input layer. So let's skip this because we don't have enough time to go through the detail. So okay, here finally the gradient descent update equations of this neural network. Sorry, yeah, neural network. But it's a MLP, multi-layer perceptron. So this is so we derive the gradient descent update equation. So this is the change we need to make for the next iteration for the W weights, and this is the change of V weights for the next iteration. And you can see it will be the sum of these. So here you can see the error appears here. And what else we have here? We have the uh, grade, the derivative of the activation functions f2, okay, times hk. Here the hk is uh, the latent feature here, or we can say it's the output of the first layer, okay. And then we can look at the delta b here. Still you have the error. So you can see the error uh, propagate to here. So you can leverage the error term here, and you still have the derivative of the activation of the second, the output layer here, and times the weight of W here, and then the derivative of F1 here, and Xi, the input. Okay, so the update term will be used in the update function here. Okay, so the delta W will times a learning rate. So you can so this is the current so this is the current WKJ, and that's the next WKJ will be the current W minus eta times delta W. So that's the update equation, and it's the same for the V weights. So you can see delta term Me here contains the error and the derivative of activation function and some other things like the latent feature or the input or the weight of other layer. So this is how neural network works. So as long as you can make sure that the error can contribute to your delta here, delta W or delta V, that's the delta parameter here, then you can make sure that the new work will uh, gradually move to the optimal point. Okay, any questions so far? So with this knowledge, you can further think about how we can make sure that the error can contribute to here. So the thing you need to do is to make sure that these terms are not zero. Okay, that's very important. So here we can see the derivative of activation. So in some cases, the derivative of activation can goes to zero. When the derivative of activation function goes to zero, that creates a vanishing gradient problem that makes your training invalid because now the error term cannot propagate and cannot contribute to the update of the parameter. So it kind of uh, slow down or even stop the updating of your neural network, so it cannot move to the optimal point. So in your neural network, it's important to choose your activation function. So here, I'll just introduce uh, some some well-known activation function. So here we have ReLU. It stands for the rectify uh, linear unit. So this formula is relatively simple. Uh, so you can see the activation R of Z. Z is the input of the activation function. So it will be just Z. It gives you the same thing if your input is positive, and it gives you zero is if it's zero or negative. And there are also sigmoid function. It's a it's a curve presented by this formula. Oh, by the way, here you have the function and the derivative. So you can see when the derivative goes to zero. So here you can see the value might not be very good for uh, negative input. If your input data to the neural network is negative, then you you will create some zero derivative if you use ReLU. So you need to be careful. ReLU is mostly for image data because image data, the value of pixels are from 0 to 255, so it's always positive. But if it's other type of data, like EEG data, you have negative values, so you need to be aware of that. Perhaps you need to avoid using ReLU for neural networks that process EEG data. And here you have sigmoid data, a sigmoid function. The function is like this, and the derivative is like this. And if you want to use ReLU, but you still want some want to avoid vanishing gradient for negative input, then you can use leaky ReLU. So here you can see you have this expression, and the derivative is no more being zero for leaky ReLU. So there are many other activation functions. These are just some well-known, but a lot of people create their activation function in their model design for some specific purpose. So some other well-known activation functions are the hyperbolic tangent and the max out and the exponential linear unit here. Any questions so far? And here, let's just have a picture to admire the three Turing Award winners in 2018. So these three are the big heads in the field of deep learning: the Yasha Bengio, Jeffrey Hinton, and Yann LeCun. Uh, so here, let's introduce LeNet. It's developed by Yang LeCun. And at the time, he was also collaborating with Yasha Bengio um, when they were colleagues. So uh, this is a convolutional network developed to recognize the handwritten numbers. So the handwritten numbers are 0, 1, 2, 3, 4 to 9. So it's an image recognition problem. Given a number image, you have to predict what number it is. So it's a 10 class classification problem. You have the input picture like this. It's 32 by 32 pixels, and using convolutions uh, within each layer. So unlike the MLP network that has perceptron nodes for each layer, here you have convolutional kernels at each layer. So the first layer is a convolutional kernel like this, and the kernel will do the convolution across the whole image to create the output of this layer. Or we can say that's the latent feature between this layer to the next layer. And then it will go through the layer by layer, and ultimately it will goes to the classification layer to gives you the output. Okay, so here you can see it's mostly convolutional layers within this networks. And there are some other design here like subsampling. I believe this is to reduce the dimension so that uh, so that can helps the learning speed and also to save some memory, shorten the computational time, or even avoid overfitting. So you can see subsampling here and subsampling here. And this is fully connection because at the end you have a bunch of latent feature. It comes with size. It could be high dimension. So when you want to summarize all the information to the output, you need a fully connection layer that can uh, integrate all the information to the classification layer so that it can output with the labels. Okay, so this is the structure of the net. And here again, let's have a review on convolution. With the convolution kernel, it will go through to go to the image from here to there. That's 1D convolution we talked about, and 2D convolution. For image processing, this is example to show how convolutional kernel works. So different convolutional kernel can give you different effects of processing. Here, here, for example, if you have a kernel like this, then it will capture the. Okay, let's make this a question. So, uh, so what type of edge can be detected by this convolutional kernel? Is it horizontal or vertical? Any volunteer want to answer? Anyone want to answer if it's vertical or horizontal? You have 50% chance if you just want to guess. Or I can okay, uh, we have volunteer? Yeah. So Liu Xuejun, this one.
This is vertical.
Vertical. Could you explain more why you think it's vertical?
Can I speak Chinese?
Sure, sure, no problem.
因为它，我想一下怎么解释。
Okay.
因为我们可以看到它这边抓资料，它是抓上下两排的。
嗯
那在每次使用这个 filter，它中间那一个横排的资料都会被清除掉，
哼，
然后只留上下两排的。那照这样子看的话，因为就经过每一层 filter，它就会截取上下两排的资料。那所以我这边就认为它会是以抓垂直方向的资料为主。
所以它产生出来的东西会形成一个，就是应该怎么讲啊？这是个人脸嘛。那个 vertical 的话，就是说人脸上面有一些边缘，它是走这个垂直走向的，然后有一些边缘是走水平走向的。所以你是说这样子的 kernel，它会找出这样子的边缘，还是这样子的边缘？
左边那一个，
左边的 vertical。OK，对，我觉得你的想法过程 OK，不过我觉得你可以再看一下说这个东西啊，它是看这边跟这边的差异，所以意思是说，就是图片它的这个上面跟下面有差异的时候，它会侦测到。那所以图片的上方跟下方有差异的时候呢，是像这种水平的边缘，因为它们的上方跟下方会是不同的颜色，所以才会被侦测到。OK，不过我觉得这还是一个很好的讨论，谢谢。Okay, so this kernel can detect the difference between the upper side, and downside. So if you have a horizontal edge here, because in the original picture, uh, this edge might be between the hair and the forehead, so they have different colors and different brightness. So for this kernel, it can detect the difference between up and down. So it will end up output with the horizontal uh, edges here. And if it goes another way, then it will gives you the vertical kernel like this. Okay, so convolutional neural network has been successfully used in image processing, and a famous image data set is called ImageNet. They have competition each year, and we can see that in 2012, there's the model gives a very little, very small error and is significantly outperforming other models. And since then, people realized that CNN can really make a very good image processing or picture or image recognition, and even more accurate than human. So we can see that the error of image net classification goes from here to here. In the 2012, the winner, this one, was called AlexNet. It's a famous convolutional neural network. And since then, each year, the development of deep learning decreased the error. And at the end, in 2015, the ResNet outperforms the human experts. Okay. So this is the structure of AlexNet. You can have more detail if you Google AlexNet, or you can start by reading the article here. I have a link here. And for the image net, it is to recognize the label of the in the picture. So here, the up four are the correct examples. So it successfully recognized the mind, the container ship, the motor scooter, and the leopard. And it also make wrong prediction at the grill, the mushroom, the cherry, and the Madagascar cat. And this is a detailed structure of the net. Uh, so Okay, so this is different from the previous LetNet. This is LetNet 5. So I'm showing this because I want to, I mean, this is same as the previous LetNet, but here I want to introduce the average pooling that's been used in a long time since LetNet been developed. And the pooling is a way to uh, reduce the dimension. So here you have a 4 by 4 matrix. And there are different ways of pooling. If you choose max pooling, then it will look for the maximum value of each subregion. So here, this part has a maximal value of 20. So you record 20 here. And here is 30. So the 30 is here. And here you have uh, 112. And then here you have 37. So that's maximal pooling. And the average pooling is to compute the average of each subregion. So you have the value like this. So you can see a difference. The max max pooling, if you compares the so we can look at the top two region here. Here, the maximum pooling gives you a higher response on the top right because there's a 30 here. But average pooling gives you a higher response on the left because the average is higher here. So it depends on what feature you try to look for. You can use different pooling. So for example, your feature map is like this. So it depends on if you want to capture this feature. If you use max pooling, you cannot get this feature because this is a lot of zeros in the image. But with average pooling, it can retain this. But if your feature map looks like this, the max pooling can nicely retain this information, but the average pooling kind of make it vanish. And there are some other things being used in the neural network model to boost the performance, like batch normalization. So it can be used for the hidden layer within the neural network, and it can uh, normalize the distribution so that the training and test can have a similar distribution after normalized. And And the assumption is that if you have a normalized if you have a normalized latent feature, it can help the gradient descent process, so that it doesn't make too much overshoot. Okay, for example, if you're hyperplane a parameter like this, it might easily, you know, uh, get it might not be easy for it to track the right pathway. If it normalized, then it can kind of make it more stable to go downwards to the optimal point. And there are dropout. This is a method to avoid overfitting as well. Since we have a lot of nodes or kernels in the neural network, and they are updating all the time. And the trouble is to to pause the update for some of the parameter, so that it does not learn so much for each iteration. And this is a way to avoid dropout, because sometimes the neural network is just learn too fast and learn too much for each iteration, and and creates overfitting. So the dropout is to randomly assign part of the parameter not to update at this iteration. So you will need to set a probability, and that's the portion uh, of parameters being freeze at this iteration. And also we have softmax classification. That's this is a very often used classification layer. So softmax will have a function with this expression. So it will gives you the probability of each case in the prediction. So depends on how many cases you have. The probability of each case are distributed like this. They have sum of one here. And so here I'm just gonna show you some of the famous model being trained and being applied in many different areas. Like YOLO is for real-time fast object detection of computer vision. And besides convolutional neural network, there are also other neural network that can um, handle other types of data. So convolutional neural network are mostly successful in image data, and but for time series data, a lot of people use recurrent neural network. And one of the famous recurrent neural network is called long short-term memory. So here it can capture the relationship between different points in the time series. And it can be used for language processing. So here you have a sentiment predictor. It can recognize the sentiment information from text. And there are also generative adversarial network. Again, this is a very important model. So it used two neural networks to fight against each other. One is code generator. This generator can create patterns from noise, and the discriminator can detect if it can recognize if it's a real if it's a real data or fake data. So, for example, if it's an image, then the generator can create image from noise, and the discriminator can distinguish if it's a real image data or a fake image data created by the generator. So the discriminator is usually very good in recognizing real and fake image at the beginning, but after training process, the generator will uh, be able to learn how to create a fake image that's difficult for the discriminator to recognize. So at the end, you will have a generator that's able to create image from noise. And this image is very similar to real image. So for example, if you let the GAN learn uh, to generate uh, zebra texture from horse texture, then at the end it will be able to create zebra texture on any horse. And it looks just very similar. And you can create fake face images. And so you've heard about the news of deepfake, that people trying to synthesize fake videos with different people's face. So this has been really widely used for its powerful way to generate fake data. And in the complementary video, I will go through the details of PhotoBank common spatial pattern. I talk about this traditional method because a lot of deep learning models for EEG are inspired by the traditional machine learning algorithm like filter bank spatial common spatial pattern. I'll explain this and then I'll explain creating a CNN using EEG next week. So in the complementary video, I will talk about the detail of the bank CSP so that you can understand the design of CNN for uh, for EEG decoding next week. Okay, so this is the end of the lecture today. Any questions? Okay, so please reach the TA if you interact with me uh, in this class. Okay, uh, if there's no more question, I'll stop here and I'll see you next week. Goodbye.